Okay, so it's time to our lecture. So okay, everyone, good afternoon, and welcome Professor Nakajima with his lecture, Nano Mechanics of Polymer and Rubber.
Okay. Can you hear me?
Yes. Yes.
Okay. So 大家好，我叫钟道坚，是东京工业大学的教授 ，right？ 虽然我每天学中文但我的中文不好 ，so now I change my the speech into English. So
Professor Nakajima, good Chinese.
was it good?
Good.
Yeah, thank you very much. So, once again, thank you very much for joining, students. Good afternoon, and also professor. So, thank you very much for introducing me. And it was actually quite the nice opportunity to give this type of the lecture in front of the Taiwanese students. I know many of you are not so familiar with the this type of material science because you are working in the field of engineering. So I try to, make my slide easy to understand. But if not the case, please allow me. But yeah, and then tell me at any time. That's fine. Okay, so today I'm gonna talk about kind of nanomechanics on polymeric material and especially on laboratory samples. So in this morning, Professor Ogisawa and Kuboyama explained about what is polymer and what is polymer processing or some kind of viscoelastic nature of the polymeric material with using many examples. But today I will further go into the nanometer scale world, which it's the range of the atoms or molecules, or a bit larger, but you start to observe the phenomena really occurring inside the material. When in your daily life, I'm quite sure you don't think about what is going on inside the lava material because you just use a lava as a component of the kind of, the engineering, the stuffs like a robot or other the mechanical stuffs. But after listening my talk, then please start to think about also what is going on inside such components. Of course, the different material behaved differently. So even in the case of polymeric materials, the rubbery state and the plastic state is totally different. But this time focusing on the rubber samples. Okay, so this is a picture of mine and taken at the conference. Then you may, after listening to this, but you may feel it's very surprising, but there is the international conference on rubbers. So it's worldwide conference and several hundred people get together from all over the world, even from Thailand, Taiwan. Yeah, so then we discuss many different type of the discussions, but basically on rubbery materials. So maybe in your daily life, people don't think the rubber is new. Yeah, rubber is actually the daily, you can find anywhere the rubber samples, but still we have a lot of issues that we can discuss as a academic, the subject, or also industrial point of views. So yeah, today you can call me, for example, just Dr. Rava. That's fine. Okay. Okay, so now let's move on to the contents of today's topic. During my lecture, I will mention several big names. For example, the Jules, he's a French scientist and maybe very famous in the field of thermodynamics. Although you are in engineering the field, but still you may heard about his research. For example, Jules heat or something like that. So he's a founder of so-called thermodynamics. Also, the Feynman or Boltzmann and some Japanese people, and you of course should know the name of Einstein. I will also talking about his achievement in the field of this material science later on. Okay, so I hope you enjoy my talk. So first topic is actually Gaffitude Effect, and here is a photo of Jules. He's the person of the 19th century, and Gaff first found this effect, and Jules made a kind of mathematical explanation on it. Then I will now stop sharing, and then let's start a very simple experiment together. I request Professor Lin to give my message to you that bring the rubber band like this.
Yes,
Okay.
we brought.
Okay. Can you distribute to the all the
Yes,
students?
yes. So
And
are they in the good size?
yeah, any size is
Yes.
fine.
Perfect, perfect. So yes, and I told the students online. I hope they have the rubber band in their hand. Thank you.
I hope so. Yeah. Okay. So after waiting a few moments, then we start this very simple experiment. And some of you may already know this, but if not the case, then please tell your friend or your family because it's really interesting.
Okay, Professor, we are ready.
Yeah, okay, then let's start. So now you have a rubber band in your hand. Then first of all, hand like this. Then first, please measure the temperature of this rubber band by bringing the rubber band onto your lip, for example. Then you can feel the temperature of this rubber band. Then after that, please slowly stretch it. Okay. Then please look at me. Then first release the force quickly and once again measure the temperature. Please look at me like this. Okay. Once again, slowly and quickly. Then measure the temperature. So then you may felt the change in the temperature, right? Was it up or down? Yeah, I think the temperature gets down, so it becomes colder, right? But then after that, then this time, just quickly stretch the rubber band. Then once again measure, like this. Then the temperature raised up. The rubber band get hotter. Could you confirm it? Right? Yeah. So this is the effect called Gaffitude effect. So then once again, oh, just a moment. It's gone. Just a moment. Yeah, I will once again share my slide. Oh. So experiment was over. It's very short experiment, but I think many of you bit enjoyed with this experiment. Then now I think you are looking at the once again coming back to this slide, and then here is the question: these lava bands get hot or get cold? Yeah, it's really depending on the process stretched or shrunken. Yeah, when the suddenly shrunken, then the lava band get colder. Yeah, that was the experimental result. Yeah. Then the Professor Fineman, you may know him because he is a very, very famous physicist, and he wrote the textbook on very basic physics. And in Japan also, we use his textbook sometime. And then you can find a very interesting experiment in his textbook. So here, there is a wheel, and these are the lava band. Then the one side is heated by the lamp. So maybe you'd better to look at the next the slide, which is a YouTube movie. Yeah, if you do so, then this system start to rotate. Very interesting. Why it happens? Yeah, but it's a bit difficult, but now you could feel that the kind of conversion between the heat and the mechanical responses. So because you have already did this experiment, you give us the mechanical stimulus, then the heat is generated or heat is dissipated. Such kind of phenomena is occurring. So then this type of the system could be produced based on this the basic phenomena. Yeah. Then coming back to this rubber band experiment, when we stretch the rubber band, then it was heated up. So let's say it's a kind of a volume change or the shape change has some relation with heat generation or heat usage or something like that. Then even if the phenomena occurring in rubber band is new for you, but the similar phenomena you have already learned similar phenomena when you were young. Actually, in Japan, the second grade of junior high school student learn about the mechanisms of cloud formation using this type of the cartoon figure and also this type of cartoon figure. You know, that usually, air contains the water vapor in it. Then if due to some the air flow from the lower side to higher side, then the pressure decreases, then the volume of that area, the air expands, then the expansion of the air resulting in a decrease of the temperature. Then water vapor start to turn into a water droplet. That is a kind of very simple explanation of a cloud formation. And if we use the technical term, then this can be called as adiabatic expansion. Expansion without getting or giving any heat from the outside or inside. That's the meaning of adiabatic. But anyway, you can now have a look at this experiment. This was also got from the YouTube. Then this guy now Now, inside of this bottle, there are the air with a full of the water vapor in it. Then he now start to give a pressure. Then once the pressure inside of the bottle get high enough and go beyond the maximum, then the explosion occurs and the inside air start to get expand. Maybe soon. Oh yes, now. So now the small the water droplet formation was made. Okay, I think this is what you have already known during junior high school student or high school student. Now, I want to compare these two different phenomena. The Gaffitude effect, it's a adiabatic elongation. Why I say adiabatic? This is just simply because we did this quickly, and also we did this quickly. Then this can be called as adiabatic processes. But anyway, elongation caused the heating of the lava band. But case of a cloud formation, expansion similar to elongation, resulting in cooling. The similar, but the result are quite opposite to each other. Why? Unfortunately, thermodynamics cannot give any answer on it. So to answer to this such a question, we need to move different science, which is the statistical physics. And maybe the engineering student do not learn the statistical physics, but in department of the physics or department of material science, the students in university, undergraduate course students usually learn about this, the statistical physics. And the founder of this statistical mechanics, statistical mechanics is the Boltzmann. And very easy portion could be introduced in high school lectures, I guess. So some of you have learned the similar. As all of you may know, the gas, air, is composed of, yes, small molecules. And he thought about in a gas state, each molecule is traveling very quickly inside the space. And like in this movie, the attack of the each molecules give a kind of force pulse, and then which is resulting in a so-called pressure. That was what you have learned when you was young. Okay. Then this is something a bit difficult, but I hope you still understand it. So each molecule has the speed. So which means that they have a kinetic energy. And this averaged kinetic energy can be written this way. But based on the Boltzmann's idea, it is related to a temperature with this equation. T is a temperature, and Kb is a so-called Boltzmann constant. And this equation is called as an equipartition theorem. You can forget about the theoretical, the technical terms, but anyway, from this equation, we know when the temperature becomes higher, then the molecules start travel more quickly, more faster. And usually at room temperature, the average speed of the nitrogen molecule is about 500 meters per second. Very quick. It's a level of sonic speed, right? Sonic speed is 320 meters per second, as you may know. Okay, so please remember this quickness. Then now the time to turn the thermodynamic story to a statistical mechanics story. So let's say that the macroscopic observation can be related to a thermodynamic related discussions, and the nanoscopic atomic scale discussion can be made by statistical physics. And the next, this equation is a kind of most important equation to combine this different world, nanoscopic world and macroscopic world. I think you may heard about this term entropy somewhere. Actually, this term entropy is used in many different fields. Of course, in the physics, chemistry, but also in the information science, they use the concept of entropy and relate this quantity as some different quantities. In physics, entropy is a kind of measure of heat. So in macroscopic field, entropy already has some relevance with the entropy. But today, I also want to connect this entropy with the quantity, so W, which means the number of the microstates. How many different microstates is possible in this system? Now, currently, you don't understand what I'm talking about. So let's move on to the next slide. But before that, please have a look at this. This is a tomb of a photo of tomb of this Boltzmann, Professor Boltzmann. And then you can find this S equal K log W in his tomb. So it's very nice. Yeah, photo, I guess. Okay, so okay. Now, please have a look at this on the slide. So assume that this is a kind of two-dimensional room. Of course, our room is three-dimensional, but it's very difficult to write a three-dimensional box. So I just wrote the two-dimensional box. Okay, and this box was now separated into small box cells. And then we can now count the number of the small box cells, multiplying this 14 and 9, it goes to 126. Then this small circle is the molecule. But as I mentioned, molecule is quickly moving inside this box, then traveling all of the areas. So if we wait for a long time, then this molecule travels all of the small boxes. So every time we look at the molecule, this molecule are located in a different locations. So, and we can say, because of this, the fast speed, when randomly, if we randomly observe this the molecules, then we can randomly observe the molecules in different locations. So, which in turn we can say the molecule can be found anywhere with an equal probability. So this means the microstates for this single molecule, small molecule, is 126. Then, if we enlarge the space, so expansion of their area, what's going to happen? of course, W increases. Then you remember if we take a log of W, then this is become the entropy. So for the gas molecules, increasing their volume correspond to the increase of entropy. Okay. Now we start to talk about the polymers. And as is introduced by the Professor Ogisawa, polymer is a kind of chain-like molecules. So the small molecule get hand in hand and form this type of string-like, chain-like structures. And finally, the length of the polymer chain become like 100 nanometer or even go beyond 1 micrometer. Such a long molecule. But story is interesting. Let's start to see. First of all, please have a look at this the cartoon. No, it's not a cartoon. Sorry, a movie calculated by the computer scientist. So this is a kind of revisit of the polymer chain motion reproduced in a computer, but which reflects the actual dynamic process of a polymer chain. When we write the chemical structure of polymer chain, we cannot expect, we cannot believe polymer chain is moving like this, but in reality, polymer chain is moving very rapidly, like this case, because this is room temperature measurement. Then if it is a gas small molecule, they travel very quickly. Only the difference is each small molecules have to take hand in hand the different the small molecules in between, but their activity should be quite same with the gas molecules. So as a result, they are really, really mobile. Okay. Now, this is a bit interesting, the slide. I really love it. I get this, sorry, this is written in Japanese, but I will explain. This was taken from the kind of entrance exam for the junior high school. So this this problem must be solved by an elementary school student. And this is I don't know how to say in Chinese, but in Japanese, Kaisei junior high school student, most famous junior high school for the high level. Then before talking about that, then let's first have a very simple question. How many ways is a shortest course from A to B? Then many of you can calculate it, hopefully. Do you? Yeah. If elementary school student may solve this problem like this way. So in order to come here, only one route, come here also one route. So to come here, one route and one plus one and two, and then like similarly, from A to B, 10 different routes exist. So this is a way to solve this problem by an elementary school student. But if you are a junior high school student or high school student, they may use this type of mathematics combination 5-2 because you know that for the shortest route there are two the up arrows and the right arrows, and then how to rearrange these two. So then the equation should be like this. So the result is of course same. But this everyone can solve this problem, but because this is a high level junior high schools, so in this problem, this rule was imposed. We have to take one step to the left, sorry. Then otherwise to the right or up. Once you add this single left step, then the problem level get very, very higher, so difficult. So think about how to solve it. We don't have time for waiting you. Then let's move on to the real story. So even if such the single left turn addition is become the problem very difficult, then how about this problem? So now this is a kind of polymer chain shape. Starting from here to end is here. The number of the molecule is 18. 1, 2, 3, 4, 5, or 19. So the length is 18. Then the distance from the start point and the end point is 8. So they have to have this type of shape. Then question is, how many different microstructures exist? How many passages exist? It's not easy to answer to this question, maybe. But if we can ask computer, then of course computer will quickly respond, give us an answer. But oh yeah, as I mentioned, how many passes, of course, correspond to how many different conformations of a single polymer chain exist. Okay, then we can now think about the easiest case. The contour length, the length of a chain is 18, and the distance between two ends is also 18. In that case, how many different microstate exist? Yes, of course, only one, this shape. No other way is possible. Then, which means number of the microstate is just 1. Then entropy is now becoming 0. Then you may know in a natural world, entropy should increase all the time as a natural direction. So this minimum value of S is not naturally occurs. Entropy is 0. So other cases, the entropy is, of course, the positive at certain positive values. So then, by comparing the case of gas molecules, this gives you opposite trend. In case, do you remember the case of gas molecule? When we increase the room for the small molecule, the entropy increased. But for this chain-like molecule case, stretched situation gives the minimum entropy, and if it is in a shrunken formula, which we call random Cohen formula, then entropy increases. So stretch situation is not good for the polymer chains. Then, so once you stretch by someone, the two teachers, then student has no freedom. And correspond to the microstate, number of the microstate is just 1 and entropy is just 0. So when the stretch situation is released, then they get back the free, they get once again the freedom, and entropy increases. So now we could see the difference between a gas molecule and the polymer chain. Why? The tendency of heat. I mean that the Garfield effect on the cloud formation give a different direction in thermodynamics. So thermodynamics itself cannot give any answer to this, but if you start to think about what is happening inside the material, then you now can explain this opposite trend. And of course, I will not go into the detail. Finally, we can write the Garfield effect in equations. So how much temperature difference we could expect, and the right-hand side is this answer. And here, S is actually the entropy. How much entropy different, then which determines the temperature difference. Okay. So this is the famous Japanese TV program in NHK. Then it's a really interesting the TV program. Then put some question, and these guests answer some question, but their answer was so stupid, and then some professor coming in and start to explain about the real answer. That is the concept of this TV program. And then anyway, please have a look. So of course it's perfectly in Japanese, so I will not go into the detail. But this time's question was, why does the lava stretch and shrink? Yeah. So her answer was, because lava is like water, she said. I will explain it later, but now you can see my face. I was on this TV program. Okay. And yeah, this is our, I'm now here in this room. And now forget, this is what I showed you before. But what I wanted to say is this virtual experiment by human being. Okay. Yeah, look, this is a kind of imitation of the small lava molecules. But once you give a kind of stretch to these guys, then they lost freedom. Then once force is released, then get back naturally. So even using a human being, then we can repeat this type of experiment. Okay. Of course, you can ask computer to do a virtual experiment. So when we start from this type of the stretched formula, then yeah, let's see what's gonna happen. So it's try to get back to the shrunken formula. The right-hand side is the distance between the two ends, and it's decreasing, and get back to the kind of equilibrium length. And in this computer simulation, I just gave the very simple rule. Ask all of the components, they can freely move up or down, left, right, if possible. If constrained, then forget about it. Then at the beginning, of course, only two ends can move. But once they start to shrunken formula, then all of the component can start to move. Yeah, at the beginning, once again, look, at the beginning, only two ends is moving. But upon the time course change, then all of the member can start to move. So once they get the freedom, then the natural direction of a polymer chain is a shrunken form. That's the reason why Professor Ogisawa's the slide, polymer chain is always written in a kind of what to say, random coil-like structures. Okay. Now, I bit talking about my research. So I'm a specialist of atomic force microscopy in Chinese character. This one. I hope some of you may know this the new technology. Also, oh, it's not new. The invention of this the microscope is 1986, so already almost 40 years ago. But still new, I guess, if you compare with the other microscopes. Usually, microscope needs lens. In case of optical microscopy, or even in the case of electron microscopies, they use lens for photon or lens for electron. But this atomic force microscope doesn't need any lens, but instead it has so-called cantilever. So just the plate with the size of like 100 micrometer, with the thickness about less than 10 micrometer. But this portion, here is a protrusive region. This is magnified image of that portion. And this portion, the top of this portion is very sharp. And when the inventor is the Binich, and this is IBM guy, and Professor Kuwait from the Stanford University, they invented this AFM. And this is a kind of cartoon figure in a first the scientific paper on this AFM written by themselves. And then they said, of course, at the top of the probe, that there would be a single atom. Then, if you can trace using this atom on the sample substrate nicely, then you can get the kind of atomic resolution images. Of course, at that moment, they could not realize such high resolution imaging. But nowadays, as is in this slide, the researcher can get this type of images. This is such kind of complicated molecules, but now we can visualize actual. This is not the computer simulation. This is real microscope images. So this AFM is a really wonderful tool to have access to the nanoscopic world. And my friend Keiji Tanaka, I think he's also very famous in Taiwan because he has so many professors in Taiwan universities. And anyway, he's also my good friend. He also uses this AFM to have a look at the, oh, sorry, this is Chinese, adsorbed polymer chains. Yes, as you can understand this Chinese character more better than I. Yeah. Anyway, he used AFM to look at the this chain-like molecules. So I remember someone put the question to Omisa Sensei that the cartoon figures in his slide is just the imagination or the observation result. And yes, of course, we can look at this type of shape. And in the case of crystalline structures, then of course we can look at their more regular shape, regularly arranged shapes. So don't worry. But anyway, this case is he just looked at the polymer chain structures strongly adsorbed on the substrate. So they doesn't move. Then my research is this. Use same AFM, but we do this in a liquid medium. Then because polymer chain is moving like this, then picking the end of the polymer chain and pull a single polymer chain. Like pulling the rubber band, we can stretch a single polymer chain with a 100 nanometer size. And original shape is just a 5-10 nanometer. Even such a small object can be accessed by this technique, and also not only just the image, but also give a kind of a mechanical property measurement. Okay, and this is a result. So please look. The length scale is nanometer, and the force level is a piconewton. You know the Newton, of course. You also use the unit as for the force. Then one Newton corresponded to 100 gram, but pico is 10 to minus 12. So how small is it? But still, AFM can detect such small force response upon a stretch. Okay. Sorry, just a moment. I forget. Yes. Okay. I will bit continue, and then move on to the short break. So this is the one example of polymer nanomechanics, which is my expertise. Then, because the small chain-like molecules, full of this rubber band is full of chain-like molecules in it. Then how to connect such small world on the macroscopic rubber band? We also have to think about or make some the mathematical formulas. And of course, there are so many researchers working on it. And this Professor Kubo is one of the pioneer in this field. Professor Kubo is one of the worldwide famous professor in the field of statistical mechanics. I think everyone in this field in the world know his name. But very interestingly, he wrote the textbook entitled with lava elasticity. This is Japanese, sorry, but this is elasticity, you know. Then this means lava. In Japanese, gomu. Okay. Then, very interesting things that he wrote this textbook when he was 25 years old. At that moment, he was already a professor in a University of Tokyo. Such a clever professor existed in former Japan. Then, what I wanted to say is that he's a big name in the field of statistical mechanics, but first interest was placed on rubber. So rubber is such interesting material in terms of the statistical physics, thermodynamics. That's the reason why I'm also doing the research on rubbers. So, because it will take some long time to discuss such kind of bridge between nanoscopic and macroscopic, so I will not go into the detail of this discussion. But as is written in the Kuboyama sensei's slides, in the last part of his slides, and also here, the lava is a kind of the cross-linked the chain-like molecules, like in this cartoon. So each polymer chain is cross-linked by using some chemical stuff and form, although this is two-dimensional, three-dimensional network-like structures. Then, because as we saw, that even in a single polymer chain can have a elasticity. Once stretched, then the naturally get back. So the group of such the molecules can also exhibit the similar property. That is a lava elasticity. So now I think you have already understand why lava gets shrunk. The reason, answer is because each component, I mean that the single polymer chain tends to shrink naturally because of entropy. That is answer, okay? So this is once again the simulation movie of this lava, inside of lava. So each blue lines expresses the polymer chains, and one of which is now expressed by the green dot. So in this way, inside lava, polymer chain is very rapidly moving to exhibit entropic elasticity. So this means, this is very important. You may thought up to now, lava is solid, right? But by looking at this and after listening to my lecture, you can say yes, that lava is microscopically liquid. If it is solid, the atoms never moves so rapidly. Only in this lava, small components quickly moves, like in the case of the water, other organic solvents, any kind of liquid. So, which means that the nature of lava will be quite similar to water, which we will look at later on. Okay, so yeah, from here, we will have different topics. So why don't you have like 5 minutes break? Is it okay? Any professors? Oh yeah. Is it all right to take?
Yes, the time arrangement is good. Yes.
Thank you.
Yes. Thank you. So let's take a break.
Yeah.